care of the safety meeting. I'm gonna take care of the safety meeting again today, guys. And we will start back to letting you guys do the safety presentation, starting after today. So anyway, being that the days are getting hotter, it's a lot of humid. I picked out a video that talks about heat stress. It's a pretty good video. I caught part of it. That's something that you really need to watch out for, guys, is your body heat. Make sure you hydrate. We talk about that a right good bit out there, but you guys see my screen?
Not yet. Here it goes.
Yes, sir.
Got it. Came up.
All right. As soon as I can get this out of the way. There it is.
I got that.
Who is that? Lenny?
Yep, Lenny Kravitz.
All right, guys, here we go.
Exposure to high temperatures or heat can cause serious illness and even death. Ensuring that your body is regularly hydrated and protected from sun during hot months is essential to maintain balance for performing well at work. Risk factors for heat illness include high temperature and humidity, direct sun exposure, no breeze or wind, low liquid intake, heavy physical labor, wearing non-breathable waterproof clothing. No controls are in place to reduce the impacts of equipment that radiates heat, and the worker's body not being acclimated.
Okay. Got these things. I'm going to stop it right here, right now, and just let's look at these factors they're talking about for heat illness. Of course, right now we're in, the temperatures are starting to climb again. We're in high humidity. You're in direct sun out there just as that. A lot of times there is no breeze where you're working. Dehydration, you don't want to get caught dehydrated. Heavy physical labor. We're going to start getting into more of replacing these poles, climbing, rebuilding. So there's going to be more physical labor to what we're doing. The clothing is really not so much an issue right now unless you make it. But when you go to work for a utility, you're going to be wearing FR clothing. And of course, that's going to be very thick clothing. And it can be very restricting. Equipment radiating heat now that we've got the equipment back on the field as well, line truck and a bucket truck out there, being around those pieces of equipment, they put off heat, especially when you're on the job and you've got several pieces of equipment out there and you're working there, pretty much surrounding the pole and all the works in between all the trucks and the exhaust and the heat and all get to you. You got to really watch out for those kinds of things. And then, of course, it's like I used to work with a guy when I started. He came out of a grocery store and he cut meat for a living. So he was in a controlled environment, very cold all the time. And he came out to the heat. And the first summer that he was with us, he about monkeyed every day. I mean, that's just something. You just got to get your body acclimated to the weather as it changes. So, and especially coming from, a cool environment into the heat and humidity we have here, that sometimes it takes a little while for us to, get acclimated into the heat. So these things those are factors we have to look out for whenever we're on the job and working.
I'll let you know something happened. Professor V wore his hat yesterday.
Yeah.
And I didn't, and because it's pretty overcast and breezy, that direct sun exposure, I don't think that a cloudy day is not going to get you sunburnt. My forehead is scorched from yesterday, and it wasn't really all that sunny yesterday. So make sure you need to use sunscreen cover when you need to, hard hat or a hat or something like that.
Yeah.
Just a moment to touch on that non-breathable clothing.
Mm-hmm.
We'll talk about fire retardant clothing and the different voltages and different type of clothing you need. Sometimes you're going to have to wear layers of clothing.
Yeah.
Depending on the voltage. And I mean, what we did is we had a FR uniform, and if we needed to work in a pad mount transformer on the ground, and it was a specific voltage, you'd had to put on a bodysuit.
Mm-hmm.
So you got a bodysuit on, you got your protective clothing underneath that, and the bodysuit was fire retardant, and you got your rubber goods on. Guys, it's 100 degrees outside, and you're dressed for winter. So that's a biggie right there.
Yeah. All right, rolling on.
To working in a hot environment. And the risk level increases with the heat index as well. So caution must be taken anytime the heat index is above 91 degrees Fahrenheit. Following are the two most serious illnesses that may result from exposure to heat in the workplace. First is heat stroke. This is a medical emergency that may result in death. Signs of heat stroke include confusion, loss of consciousness, and seizures. If a worker shows signs or symptoms of heat stroke, get medical help immediately and call 911. Heat exhaustion is the second most serious heat-related health problem. The signs and symptoms of heat exhaustion are headache, nausea, dizziness, weakness, irritability, confusion, thirst, heavy sweating, and a body temperature greater than 100.4 degrees Fahrenheit. There are precautions that can be taken when temperatures are high and the job involves physical work. First is hazard identification. Learn to recognize hazards such as high temperatures, humidity levels, sun, and other thermal exposures, work demands in clothing or PPE risk factors. Next is using heat identification tools to evaluate your environment on the job site, such as OSHA's Heat smartphone app or the National Weather Service Heat Index. The next precaution is to block out the sun's rays. Another is to cover up. Wear tightly woven clothing that blocks out light. Try this test. Place your hand between a single layer of your clothing and a light source. If you can see your hand through the fabric, the garment offers little protection. Use sunscreen. A sun protection factor of at least 30 or higher is recommended. You want to block both UVA and UVB rays with a broad spectrum sunscreen to guard against skin cancer. Be sure to follow application directions on the bottle. Wear UV absorbent safety glasses. They don't have to be expensive, but they should block 99 to 100% of UVA, UVB radiation. Wear a full brim hard hat to keep the sun off your neck, ears, nose, and scalp. Limit exposure. UV rays are most intense between 10 a.m. and 2 p.m. If you're unsure about the sun's intensity, take the shadow test. If your shadow is shorter than you, the sun's rays are the day's strongest. Next is hydration. Hydration is crucial to limit heat stress. Water should be available and easily accessible. The exact amount of hydration intake depends on the individual, but a rule of thumb for an active construction worker is to drink 32 ounces of water an hour, which is about 1 cup every 15 minutes. Also, replace necessary electrolytes the body needs to stay hydrated, fueled, and focused. And avoid alcohol and caffeinated beverages. Both lead to dehydration. How do you know if you're dehydrated? Use a dehydration urine color chart that uses your urine color as an indication of your level of dehydration and what actions you should take to help return your body back to a normal level of hydration. And finally, rest. Consider a modified work schedule, such as starting early morning and finishing early afternoon, to avoid the hottest times of the day. Take rest and water breaks when needed, and ensure that fully shaded or air-conditioned areas are available for periodic resting and cooling down. Workers not used to working in higher temperatures need an opportunity to acclimatize over a period of up to 14 days. This process gradually allows the body to build a tolerance to working in the heat. If a worker falls ill from heat stress, immediately get them to a shady or air-conditioned area. Provide cool water and apply ice to the back of the neck, and immediately contact a supervisor. Working safely, especially in high temperatures, means being prepared. Knowing how to limit heat stress may save your life.
Okay. Pretty good video, good information there. What we did at Duke, and I know they go really in depth when we do our pre-job briefs before. We have, I'm gonna unshare this screen right here. But what we had this book. It's a pre-job briefing book, guys. Inside of that book, it had a hydration guidelines, and you can see it right there. There's 2 pages with it, and we actually had to assign somebody as a hydration coach during, very hot days like what we're going to be experiencing through the summer. And that was kind of seems kind of silly at times, but really when you're working and a lot of times and you starting to get overheated and you got somebody working next to you and they're noticing that, hey, you're not sweating as much as maybe you need to be, and you need to hydrate. That's where these people come into play to notice these things that are that could be affecting you and affect you through the rest of your summer, working. But we had these hydration guidelines to go by, and depending on the temperature, and it tell you how much if the temperature was 91 to 95 degrees and your work level is normal, then you needed to take a break every 45 minutes and drink 16 to 24 ounces of water an hour. If it was above 96 degrees, normal working conditions, you needed to take a break every 40 minutes and drink 24 to 32 ounces per hour. And those, and that didn't mean the whole crew had to stop for a break or whatever. It just means that, your body's limitations. You see what the guidelines are supposed to be. They expected you to follow those guidelines to the letter, really, just so you stayed hydrated, so you stayed healthy throughout the day. Because if you start getting heat stressed and really get sick, I mean, that can have long lasting effects on you, especially through the summer. You get hot again, and it doesn't take but a minute for you to get overheated, and your body just kind of reacts differently after that first initial time of being overheated. As well, not only that, you got heat rash, heat cramps, heat exhaustion, heat stroke. All those things are signs that you're being dehydrated. And not only that, you need to make sure you drink enough water. There's a chart we had on the second page. I don't know if you can see it good, but it's kind of gross, I guess, if you want to say it that way. It's a urine chart on there you can look at, and you can see the orange and the yellow. If your urine's like a darker color, you are definitely in need of hydration. And that's either water, electrolytes, Gatorade, Pedialyte, whatever you got to drink. You want to stay away from the caffeine drinks when you get in those situations, and drink clear liquids or, the Gatorades and kinds of things. So, I mean, there's different things that you can do, different kind of things. Back in the day, we used to do salt tablets, which we don't do anymore. They used to feed them to us like, aspirin, but that's not the case anymore. We don't do that. We do the Gatorades, the Powerades, and those kinds of things. So, good video. Need to watch your heat levels next coming weeks. I think it's probably going to start getting hotter, as you can see in the Midwest and those parts of the states right now. They're going through a heat wave. I don't know if we're going to be getting that much, but it's pretty warm out there in the afternoons now. So we're going to pay close attention to it and make sure we're all hydrated. Professor Shoemaker.
I mean, a lot of great points in there. When you look at the temperature for the day, check the heat index. Don't check the heat.
Yeah.
I've seen some 95-degree days that the index goes to 103. So make sure you check the index on that.
Yeah.
As far as your hydration is concerned, it's very hard to catch up.
Yep.
So if you start, and you saw that urine chart he showed, I mean, you go to the bathroom and you see that getting darker, and it's hard to catch up with that. If you drink a couple bottles of water in the morning, expecting a heat day, and continue, I mean, you'll be much better off. It's kind of, and I've seen in hot summer days, I've seen the workforce go down. Heat cramps, heat exhaustion, Some have been taken to the hospital and have, you know, intravenous fluids. You're losing people in that situation. And you remember what we talked about in the field yesterday? As far as your work is concerned, me as a supervisor, what do I want you doing? Stay busy, stay constant, have something to do all the time, right? You guys are going to have to self-monitor in those situations and let your supervisor or fellow employees know, you know, it's getting hot. Let's tone it down a little bit. Now, this sadly is part of the industry. Those heat indexes go up. What happens to your customer base? What's happening with the power on your system?
It's being used.
Down. Your outages are going to rise.
Yeah.
Okay. You know, in the when you have severe cold, we're going to talk about hypothermia. When you get severe hot, we're going to talk about heat stress. So really, you got to push a little bit harder. And I have seen situations, I'm sure Professor V has also, where you're going to have your coordinators or company call customers back and say, look, we've got to focus on the customers that have power already to restore outages. And we're going to have to delay that scheduled work for you to be able to keep our system up to par. So it's counterintuitive. Here on one hand, we're telling you, you know, one thing, and on the other hand, your outages and your trouble calls and your request to do more work is higher. So, you know, self-monitor, watch yourselves in those situations because it can get quite tough. There was only one other thing I could probably think of in that video, Professor V, is cotton clothing.
Yes.
Yeah, cotton clothing. When you're underneath your fire retardant clothing, you would think this is kind of strange. You got fire retardant clothing on. If you wear a shield, I would say in between of full cotton clothing, it does keep you cooler. Okay, it has to be 100% cotton underneath that fire retardant clothing to meet FR capabilities. That's the socks, underwear, and shirt.
Yep.
There was one other thing I was thinking of, and I can't. Oh, I've seen a lot of people do this, and I've seen a lot of people get sick real quick from it. Don't work out in the heat and get sweaty and get hot, and you're feeling good, and jump in a 60-degree air-conditioned truck.
Ooh.
Right? You would think that would help you out. That's a shock to the system, guys. Try to, you know, kind of temperature down before you get in your fleets. Don't pour ice. Don't pour cold water on yourself or anything like that. Regulate. Do it slowly. Don't shock your system by going from severe heat to severe cold. That'll tear you up.
Yeah.
Yeah, that's a high difference of potential right there.
Yeah. Exactly. Okay. Any questions out there by anybody? Last but not least, and I told you at the start of the class, if you start feeling ill and you think you're starting to have symptoms, you know, dizziness, lightheadedness, dry mouth, you're not sweating anymore, don't go off somewhere and not tell anybody.
Right.
On the job or in my class either. Let somebody know and let them monitor you until you start feeling better. Just don't go sit in your car and pass out on it. Okay. No questions? Okay. If you can, I'll start on my side. I had some students the other day or yesterday asked me, can we review the last quiz? I got a couple questions wrong, so I'm just going to share a screen here real quick. It is an actual student quiz, but I'm not going to show a name. And we're going to go review that quiz here real fast. All right, so let me get a share screen going. Let's see. Let me know when you're able to see that.
It's coming. It's coming. It's coming. It's not coming.
No?
Not yet. Not yet. Got it.
Okay, for real. All right, so question one, and if you got any questions, anybody out there, stop me. In the electrical utility industry, what types of electric method is used? And you had the choices of AC and DC. Electrical utility systems are predominantly AC, alternating current. Okay, like I said, I'm not going to say names here. AC electricity is blank, meaning it travels the conductor in two directions. Okay, ascending means that sine wave goes up only. Descending means that sine wave goes down only. Bidirectional, which pretty much the answer is in the question, by 2, okay, is your answer right there, bidirectional. Insulators enhance the flow of electricity, obviously false. Conductors have a very low resistance to the flow of electricity. That is true. You don't want resistance in a conductor, so it is very low. A semiconductor resistance decreases as it's heated. Perfect, true. Amps, current, refers to the flow of electricity. It's great. Volts refers to the pressure of electricity. Watts refers to the usage of electricity, like in my home. How many watts are there in 1 horsepower? 745.7. If you put 746, we'll let you go on that. And what is the electrical frequency of the United States? 60 hertz. Okay, any questions there? I think the ones that got a lower grade realized the ones that they got wrong. So I'm going to stop that share right there. Okay. No questions on that. Professor V and I were talking earlier this morning. We're going to press a little bit today and hopefully knock out 2 quizzes in one session here, because you got the majority of the information for the next one. That would be quiz 2, right, Professor V?
Correct.
Now, we're going to review quiz 2. We're going to get into quiz 3. And what we'll do here, as far as assigning those, is quiz 2 and quiz 3 will both be extended until Thursday midnight. I think that's pretty fair, don't you, Professor V?
Absolutely.
So see, it's how we're given 2 quizzes on one day. We'll assign 2 on one day, but you have until Thursday midnight to complete both of them. So that's going to be 20 questions total. How about that?
Can.
Okay. All right. So while we have you out there, let's see some faces. I see about 5, and the rest of you are in the dark. There we go. Wow, ow. Predator. All right, let me get back. Golly, Professor V, my computer is grossly slow.
Uh-oh.
All right. There's 2.
Let's see. 2
So let's refer to the
quizzes.
book here real quick. Let me check this one. All right, so we talked, while I'm on that, just to get a general idea here, how's everybody doing on their projects?
Just started it.
Okay, but progressing?
I saw mine last night. I'm doing pretty good on it.
Okay, okay. Just a reminder, that's due Friday morning,
Okay.
okay, 8 a.m. If you have questions, remember, we're here in the afternoon. All right. Okay. So let's jump to the book here real quick. And there's some things actually that we can skip. I'll give you a page here in just a moment. We've talked about volts, amps, watts, their purpose. We had that in the last quiz. We talked about horsepower. The next part of the book, we're on 37, and we're going to move a little bit quickly here because we've already done work on this. I just want to remind you, it's in this book, is Ohm's law. So the Ohm's Law chart, you guys know how to refer to it. Remember, in the industry itself, or when you're doing any type of calculation, you must have two values to be able to calculate the third. And what do I mean by that? Well, you've got to have an amperage value and a voltage value to determine a wattage value, P. You have to have a wattage value and an amperage value to find R. So two values have to be measured out there to find the third. That's how Ohm's law works. Where do you get those values from? Measurements or calculations or numbers that are given to you? Or, I mean, the referral there that works the best a lot of times is the transformer nameplate. You're already given two values right on the nameplate of the transformer itself, voltage and what? Wattage. Remember, KVA for us, as Lyman is concerned, refers to wattage. So I have an E and a P, and then I can do other calculations off that. Okay, page 43. Let's go over this real quickly. Resistors. Now, do we want in our industry, both transmission, distribution, all the voltages right down to your house, do we want any kind of resistance in our industry?
Some.
When you say some, why would I want some resistance in my industry?
Well, you need
I mean, you
something to
can't have-
restrict the flow of electricity into a customer's house.
I think I know where you're going, Embry. I mean, because of the conductors themselves, you are going to have inherently some type of resistance. But do we want to include resistance on our utility, or do we want to get it down as low as possible?
Low as possible.
Right. You want resistance as low as possible in your industry because the flow of electricity is impeded by resistance. And when it's impeded by resistance, heat is produced. And then, you know, your customers are not getting the bang for the buck. I'm going to show something here real quick as far as resistance is concerned. And this, Professor V, I mean, I know you've done this before and you've seen the videos for it. You're actually going to scrub areas where you make connections.
Yes.
And make that connection as clean as possible. So I'll give them the share screen now. And you want your system to be efficient. I mean, that's just plain and simple. You would be very, very surprised. I'll show you some images here. Wow, this is slow. Oh, this is perfect right here. Open image. So this is an infrared shot of a substation and the connections inside the substation. So you'll notice right here, the center bushing on this transformer, there's a large transformer. It looks like it's doing a pretty decent job as far as emitting heat. And the heat is produced by resistance, right? Either not a clean or tight connection right there. Look what's happening over here. All that heat is being produced and just dissipates off. And on the other bushing of the transformer right over here. And you'll notice on this side right here, we have some conductor jumpers that are going from one side to the other. Pretty much, I can tell you right here what the problem is. These conductor sizes are probably too small. This conductor size is big, allowing more amperage to flow. These are too small, and obviously they're going to heat up. Now here's the million-dollar question. I'm producing and generating electricity at my power plant. How am I getting paid? How is the industry making money? Where is it making it at? Better question on that. How's it being measured at the customer?
By a meter.
By a meter, right? That meter turns, it uses a certain amount of kilowatt hours, and I charge that customer for the use of that power. Who's paying for the heat emitted right here?
the electric company.
Exactly. It's losses. And I mean, it can amount to, on large systems, millions of dollars of losses in electricity because I have a high resistance system. I'm producing heat, and that heat energy is just lost money. So industries, utility industries focus a lot on making good, clean, tight, and torqued connections. You'll run into that. Okay, any questions as far as resistance? Remember, when you're out there in the world, don't tighten something up and just kind of hand tighten it. You're going to use a tool, make it tight. That lowers resistance. You're not going to take one conductor, splice it with another conductor until you clean it first. And they actually do this out there, even when it comes off the reel. You're doing a brand new installation off the reel, and you need to make a connection to that conductor you just installed. You got to scrub it even after it sat on the reel for a while. So that they are very proactive about it. Resistance is the utility's arch nemesis. All right, so let's stop that share here. If I can find my mouse. Okay, so let's move on. Resistors. We do not use any type of resistor as far as electrical alignment is concerned, and we want to limit the amount of resistance in our system. So we're going to skip all the way through resistors. It is not on a quiz. You might see the question, is it detrimental? But we're not going to need to know anything about color codes or bands or anything like that. All right. Bless you. Let's, what time we got?
We're looking at 8:36.
How does it end up 8:36 every day? It must be a habit nowadays. Let's go to 8:50. Let's take a little break here, and we'll come back and start talking about electrostatic and electromagnetic energy. 15, 14, really. Okay, so it's 8:50. We're going to return and go ahead and get started. And the next portions we're going to talk about here are electrostatic charges and electromagnetic energy around a conductor. I'm on page 76 of the book, and I'll just read a portion of it here. Static electrical charges are common occurrence in everyday life. Almost everyone has received a shock after walking across a carpet and then touching a metal object, or sliding across seat covers in a car and touching the door handle. And when we talk electrostatic electricity, is that AC or DC?
DC.
Yeah, DC voltage. And it really is the difference between a positively charged object and a negatively charged object. Now, it's the field, electrostatic energy and electrostatic field of that voltage that's being emanated. There's no current flow here, gentlemen. When we have electrostatic energy move from one point to another, there's no flow of current. It's just the difference of potential. And I know we've spoken before, when we talk potential, when we talked about those earlier in the course here, that's about voltage. And I have a difference of voltage between one point and the other with no flow of current. That's electrostatic energy, and it's DC voltage. You guys remember the helicopter lineman?
Yeah.
Yeah.
When we had our helicopter lineman, and he approached, and this is really prevalent when the higher the voltages that you go, he had to make up a difference of electrostatic energy. There's no current flow there, but there's electrostatic energy. And I liken it to the pressure. Voltage is pressure. on the conductor itself is emanating an electrostatic field. The pressure is so high that it's trying to escape the conductor. And you saw the distance that he was when he had the wand and he came close to the conductor. You know, that was 2 or 3 feet, correct? You saw that electrostatic energy until it was balanced out and he made full connection with the conductor. All right, that's why he's using the wand. I know you guys have slid out of the car or got out of the seat and touched the door handle. It's going to kind of zap you a little bit, right?
Yeah.
Yeah, think of that in the scale of a transmission line worker. You saw how that arc that he was drawing right there, that's an electrostatic arc, no current flow. That would chatter your teeth rather hard. So the electrostatic field really in the world out there is relatively small. The higher the voltage, now you got to pay attention to what I'm giving to you here, voltage, the more electrostatic field you're having around a conductor. Now, I'm sure Professor V has done this before. I kind of like doing it too. 7200, does it have an electrostatic field around it?
I would assume so.
Yeah. Every conductor has electrostatic field around it, the pressure of the voltage that's in the conductor, but the intensity is determined by the voltage itself. Very high, big field. I've taken it at nighttime. You take your pliers in a bucket truck with your rubber gloves on, and you can bump that conductor. And I mean, gentlemen, you're going to get an electrical, you can see my fingers right here. You're going to get an electrostatic arc that's about that big. And you just draw your pliers away and it goes away. So that's real small, lower voltage. You do it enough, sit right there, the bugs get attracted to it and they get zapped in the electrostatic arc. So that's electrostatic energy that's being emitted by the conductor. Difference in potentials of voltages, but no path for current flow. All right, I'm moving up to page 84. All right, this is really how industries, utility industries are able to produce, deliver, and transmit electricity and transform it. Magnetism. Magnetism is one of the most important phenomena in the electrical field. It is the force. Now, remember, highlight that word, force, used to produce most of the electrical power in the world. The force of magnetism has been known for over 2,000 years. It was first discovered by the Greeks. It was found that a certain type of stone, which was lodestone, was attracted to iron. Okay, we won't go any further in that on the history of it. Just do know that a magnet by itself emits a force, and that force is used in the electrical field. We're going to move on from that. You don't need to know the electron theory of magnetism and valence of electrons and all that kind of stuff. What we do need to know, though, is down on the page of 89. I'm going to unshare the screen.
You said 89?
89, correct. Magnetic lines of force. I'm going to stop this share and go to a whiteboard. Professor B, let me know what it's up.
Got it.
Okay. So let me get my drawing pen here. I just had it in my hand. So I'm going to draw a couple conductors here, just facing straight down the conductor. Okay, I'm going to have a line here that's energized to 500 kV. All right, we've just learned that it does, because of that high pressure right there, it does emit an electrostatic field out of that. No current flow off of that whatsoever. All right. And I'm going to just say this, I've not applied any kind of amperage to this. There's nothing connected to it. I've got voltage applied to it, but I don't have any current flow in it. It emits an electrostatic field only. All right, same conductor. Once I apply current to the conductor, or I have people that are using electricity off this conductor, it emits the electrostatic field, just as it always does, and it also emits an electromagnetic field off of it. So electromagnetic lines of force, once current is applied to a conductor, are emitted off the conductor. Now you got to pay special attention to this. The higher the current, the greater the magnetic field. Greater or larger, larger, the magnetic field is. Okay. Which is kind of obvious right here. No current flow, no magnetic field. High current flow, that magnetic field becomes larger and stronger in strength. Okay. Any questions there thus far?
No.
Okay, right. You got to remember this. Voltage, higher the voltage, the larger the electrostatic field. I'm going to apply the same voltage here to the conductor. That same electrostatic field exists, but once I apply current to it, it then emits an electromagnetic field off the conductor. Okay, and those electromagnetic fields are what they say at the bottom of page 89, magnetic lines of force, called flux. All right, we don't need to know what the symbol is or anything like that. Page 90. The basic law of magnetism states that unlike poles attract and like poles repel. Well, we understand this, and we've seen this happen already in some of our previous videos and some of our previous drawings. Clear these drawings. Our AC sine waveform, when we have that, got the positive, the negative, and the zero line, you're going to have attraction, detraction, or what do you want to say it? Attract and repel. So this is attract, repel, attract, repel, attract, repel, all the way down that waveform. How many times does that happen per second?
6 times.
Add a zero to that.
60.
That happens 60 times per second. And
Or
that's
60.
right. And that's the nature of our generation. We're using a magnet, right? To force out, force in, force out, force in electromagnetic energy. All right. Let me clear this one. And this will satisfy. Let me ask you this question. It's been asked before. What 3 things have to happen for me to produce electricity? I've got to have what?
You gotta have a magnet, a coil, and something to spin it.
All right, magnet.
Mhm.
All right, we might as well go ahead and say magnetic field. Because that's what it produces. You have to have what else?
A coil.
All right, coil. And in that coil, I mean, that intensifies it. Conductor. And then what was the last part?
Relative motion.
And then you need something to spin it.
All right, you need movement. Relative motion, that satisfies that also. Okay, you have to have all 3 of these, and then you're able to produce electricity or transform it. That's vitally important. Okay, and we know the reasons why we need to transform it. Raise
I got a question for you.
Yes, sir.
If we can transform to a higher voltage, how far could a generating station generate electricity to? What point?
If you're transforming up and down,
So say like Santee Cooper, could they generate power to Indiana?
depending on how much current's on the conductor.
Okay.
Okay, now I see what you're saying right here. Let's take this for an example. South Carolina, and that's my generating station. And if I put 500 kV on my conductor all the way to California with nothing connected, the only reason why you're going to have voltage drop all the way to California here is why? On the
Impedance.
conductor, it's inherent impedance on the conductor. Now, I don't know that measurement, but you are going to have a voltage drop because of the resistance of the conductor itself. Once I start applying amperage to it, like a substation here, 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 and here, all right, you've got to remember there's resistance in that also, plus current flow. So, and I'm just going to throw out some arbitrary numbers. I start out at 500 kV here on just the conductor itself. By the time it reaches California, it might be, we'll just give a number here, 400. Okay, nothing attached. Now I start attaching substations and I start drawing load on it. You might be maybe about 450 kV here, and we're going to say about 300 here. That's because, and think of this right here. Think of this as the water line. I've got pressure from end to end in the first scenario. All right,
Now you're
second
restricting the
scenario-
flow in the second one.
Second scenario, I've got pressure. Some of my pressure's being relieved all this way. Some of my pressure's being relieved. You see how the pressure's being taken off? So then my pressure down here at the end cannot be that high because I'm using it over here on these other portions. Does that make sense?
Yeah.
Good deal, good deal. Good question also. That scenario, when you see that, and it happens at all voltages, on a conductor, long distances, is called, and it's not on the quiz this time, voltage drop.
So at the substations, are those like miniature generating plants?
No, no. You got to consider a generating station is a place that takes one raw material and transforms it to electricity. Coal heats water, makes steam, turns a turbine, and then that turbine's in a generator and it makes electricity. Substation takes that electricity and either transforms it up or transforms it down.
Okay,
There's a difference in the two.
gotcha.
Clear all drawings. All right, so back to where we were at. So we just saw a moment ago that I needed three components to make electricity and to transform it. One was a conductor, one was movement, and what was the third?
A coil.
Conductor, that's my conductor. Movement. And what else?
Magnetic field.
Magnetic field. Okay. Well, all right, so we just talked a minute ago. I've got my conductor that's sitting out here, right? And I just told you, once I apply a load to it, what does it create?
Creates
Electromagnetic field.
It creates an electromagnetic field around it. Once I apply voltage and current, remember, current's got to be involved here. I got to have usage. It provides an electromagnetic field. All right, so satisfied. All right, obviously, conductor, satisfied. Where's my movement coming from?
movement is coming from
Whatever resource.
motor. Whatever the generator.
No,
Steam or water or
Yeah, turbine, a diesel engine.
okay. So you see my conductor that I have sitting here right now, and I'm going to draw this. Right now, as far as current, remember this is an AC sine wave, and it shows the movement of current, even though my voltage applied right here. At the point in time, now think of this as in the time sense. Right now, the electromagnetic field you see off the conductor is right here. Bang, just where I drew the arrow. Once it goes down, how intense is this magnetic field going to be?
it drops.
It's going to, okay, once it gets down to here, am I going to have an electromagnetic field at all?
No.
No, okay. Once it starts to rise back up, is my electromagnetic field going to grow?
Yes.
Right,
Yeah.
until it gets big. So I'll ask the question again, where's the movement?
Oh, okay.
At the peaks.
It's growing, guys, in the sine wave right here, because of the method I'm generating at. Is it growing, then shrinking? Growing, then shrinking, my electromagnetic field. on the conductor.
Yes.
Yes.
Yeah, if I could take this, and I don't know if you can see me, if I could take that conductor right here, it's growing in, growing out, growing in, growing out, growing in 60 times per second. So where is the movement coming from?
I mean, it's not.
I guess I don't understand what you're saying.
How am I getting
that.
movement of the electromagnetic field down my conductor? Is it growing? Obviously, we have figured out, and I'm going to take this pen right here, go down and think of this, and we get my film. It's growing, shrinking, growing, shrinking, growing, shrinking 60 times per second. Is that movement?
Yeah.
Yes. So it's the
Okay.
conductor.
Where is it coming from?
The electromagnetic field
No, that's the field itself. How am I making movement?
by spinning the conductor.
No, the conductor is static. I can't have a spinning conductor out there in the world. And think of this guy that was on the transmission line. It's inherent to AC electricity. That's why AC electricity is so important. All right. It comes from the AC sine wave.
Okay.
Wait,
It
wait,
grows
wait.
and it
Yeah, but
shrinks.
we're talking about a mechanical movement here, aren't we?
No. Okay. It's not
Yeah,
mechanical. I'm glad you asked that question. This is not a mechanical movement, and you don't need mechanical movement.
But yeah, I mean,
You need the
so what does the turbine do? The turbine is a mechanical movement.
That is a mechanical movement. And that's in generation. What am I doing in transformation?
Oh, okay, okay. We're talking about transformation. All right.
Okay.
The generation. I'm sorry.
All right. What am I doing in transformation?
Turning it from a higher to a lower or a lower
There
to a
you
higher.
go. There you go. Your magnetic field intensifies and it goes down, back, forth, back, forth, back, forth, 60 times per second. That is the movement that we need to have. And when I say produce electricity, you guys got to remember, this is my transformer coil on the primary side. This is my transformer coil on the secondary side. There is no contact between those two coils. They're not moving. All right, they're not moving against each other, back and forth, back and forth. They're a static piece of equipment right here. But in order to produce electricity on the secondary side, I've got to have movement. Where's my movement coming from? The field gets big, gets small, gets
The
big,
sine wave.
gets small, gets big, gets small. Correct. Now I have electricity on the secondary side. Question, and this is, I'm going to throw you in the complete opposite direction. Remember when we talked about before, am I able to convert DC to DC or DC to AC in a transformer, not in an inverter, in a transformer by itself?
Oh, yeah.
No.
No. Why?
Um,
Here's my DC wave. Right here on the top.
these- I guess it.
Is it moving?
No.
It's static, no movement. I can't satisfy what I need to satisfy as far as making electricity. There's no movement, so I'm missing a piece. It can't happen. Pretty deep, huh? Let me cue up a video here, okay? Real quick. Might take a second. Get rid of that one. Professor B, you know the one I'm going to get, don't you?
Okay.
Yeah. Come on, computer. All right. Why would you? Wow, this thing's slow. Let me unshare this one. I speed it up a little bit. Yeah. That's, you know, when we talk about the transformer itself and the production of electricity on the secondary side and why they're so effective, it's because there's no mechanical movement. The movement of the sine wave at 60 hertz is an electromagnetic motion. There's no mechanical motion. So let's see how we do this. Line induction. There we go. I'm sure we'll find it right here. It is. Pause that. Okay, I'll get another share screen going and I'll give you the scenario of what's happening here. We get into ELW 231. This is going to be emphasized a lot as far as safety is concerned. Let me know. Got it? Okay. So you can see the description right here. The guy in the bucket truck is in the process of grounding a 500 kV power line. So let me get to the start of the video and I'll show you how it lays out. Should this tactical zoom lens be made illegal? You guys hear that okay?
Low.
Right, hold on. All right, so everybody see that picture that's on the screen? I know it's a little bit small. You got that, V?
Yep.
Okay, guys, right here, this guy is what he's in the process of doing. He's got a jumper that's going up to a ground on the pole. He's got a de-energized circuit right here. So he's working on a de-energized line. And he's got 3 sets. He's got 2 here off screen, and 2 more off screen of a transmission line. The line that's behind him is energized. So those 3 wires and those 3 wires, and there's another set that's hidden from view, you can't see it from view, are all energized at 500 kV also. So important here, this line is de-energized. Watch the video. Wow. Okay, so I'm going to unshare that. I'm going to throw a drawing out here.
Is that because of the electrostatic from the other 500 kV lines over there?
Hold that question. And I want you to think a little bit before I answer you. Okay, so let me clear this one off. We had just learned, let me throw a couple conductors up here.
Mhm.
All right, we have just learned before that our electrostatic field, and you saw by the videos of the helicopter, is relatively what? Size-wise?
Small.
Small, okay? So I'm gonna leave that right there. I'm gonna go and just give you close to what he's working on right there. All right, that's the conductor he's working on. It's de-energized. Here are the conductors that are behind him. They're energized to 500 kV, okay? And they have current flow. All right, so what's happening here? Is it electrostatic energy that's getting over to that other line, or electromagnetic? We know now electrostatic only go about 3 feet. From the video we saw.
Oh, it's electromagnet.
Right, right. I've got electromagnetic lines of force.
That's
They're
crazy.
when I like to use that term, cutting across the conductor. All right. So I've got a conductor, right? I've got movement because AC does what? Moves back and forth. And what's the last piece that I need?
Movement, a conductor, and magnetic field.
Magnetic field. There you go. Here's your magnetic field. It's moving in and out. It's cutting across another conductor. What you saw in that video, guys, is a rudimentary transformer. You saw a high voltage on one side. You saw no voltage on the other side. All right. It's creating a magnetic field, and once it cuts across the other conductor, produces a voltage. And I mean, that voltage that he is working with there, as far as trying to ground it, is deadly. So that'll let you know. I mean, that's just proof in the pudding there. I've got voltage, I've got current flow. Okay, I've got a magnetic field. And AC electricity rises and falls. That magnetic field moves in and out. And that's how that electricity is getting onto the other line. That's how you have voltage on the other conductor. Okay. All right. I know we spent some time with that, but that's vitally important into knowing how we can transform, one, produce, generate, and transform electricity. What time are we holding there, Mr. B?
9:19.
Let's take 10 here. We'll push it to about 10:30. So let's take about 10 minutes on a break, and we will come back.
Shoemaker. Mr. Shoemaker.
Yes, sir.
Hey, remember, so you were going around that slide where it says,
I haven't produced any slides.
I'm sorry, it was the last class where about generation of meter. The
Oh yeah,
example,
the slideshow that I showed you.
yes, where it said that a substation or it's meant to transfer AC and DC, and you said the DC was wrong.
Correct.
Yeah, I mean, well, I don't know. I did like a little research and I found out they actually do use DC, but not here in the United States. It's like in
Well, my plans were for you not to have to work overseas, but
yes, sir. Yeah, they I think they use it to transmit bulk voltage. Then they'll convert it back to the AC side.
yeah, very inefficient.
Yeah. Some people would say.
All people would say.
All right.
Every damn one of them says it.
I did tell you at the beginning of the class, DC will travel longer distances, but you're gonna have to invert it to get it back up to AC. So it's very.
Is there a lot lost during inversion?
Well, think of the process right here. You're losing about half. You're gonna be dropping about 50%. Where you have one single waveform, you've now got to invert that waveform to a lower and an upper, a lower and upper. It's about 50%, and that goes through. I mean, I'm not going to get into inversion or solar panels. Solar panels do it, right? So your solar panels, you're charging up a set of batteries, and you got to use an inverter to get AC out of it. That's one of the major causes why solar is so inefficient. But yeah, you're losing a good bit of power because you're having to invert into another sine wave. Is it okay if I take a break now?
There you go.
Okay. Okay. Let me do a little check here. Make sure we're tracking. Am I still in share? No, I'm not. Can't find my mouse though. Where'd it go? There it goes. It's that. All right, so V.
Yo.
Okay, we got that. It's true, false. Let me double check these real quick. Yeah, they just need to watch the wording on some of these questions. Got that one. Got that one. Got that one. One, that's 8, 7. All right. I'll touch on that number 7 again. 8, I mean. I know Lenny knows it because he came back and we discussed it for a long time.
Okay. Nancy.
Got that one. No, we don't have that. Okay, so I'm going to go over a couple of things here that on quiz 1, then we'll move over to more stuff and then go over the stuff that is in quiz 2. I'm going to start a share screen here for a couple of these questions. Get rid of this. And wow, slowly. Just to make sure, it's been a couple of days since we discussed it. Here. All right. Should be seeing a share screen up here.
Yep.
Okay. So you guys remember the generator, that little image that I had that I shown a good while on the screen right there, where the magnet was spinning around inside of it, and it had the three phases A, B, and C. A, B, B, and C, C. Then we had the magnet that was inside of it. I'll put a north and a south here. And this was spinning in a rotation. I know I got my letters out of sync here, but it really doesn't matter for the essence of this question. And remember, when we had our sine wave coming off of it, and I'm just going to put one phase, A, right here. When were the lines, when were the voltages most intense?
When you matched up.
Right. So if you look right here where I've got my magnet, right? This is when it was the most intense, correct?
Yeah.
And that was that point in time where I'm going to say it's right here. You'll notice that the magnet itself is in line with, correct, A phase. So as far, and this is going to go for a magnetic field or an electric coil, because we're going to talk more further on that later on. The intensity of a magnet itself, let me go back to the question. I'll just go ahead and ask the question outright, and you guys can go ahead and throw me an answer here. With a magnet, the strongest lines of force are at each end. True or false? Are the strongest lines of force here or on the side?
On the ends.
On the ends, correct.
The end.
Right. So those are the strongest lines of force coming out of a magnetic field, of a magnet's property itself, not off the sides. In fact, they actually go completely around and really get de-intensified or less intense right there at the middle. Okay, so that satisfies that one. If you need to refer back to that video. What did I say the other one was? Oh, okay. All right, so let's talk a little bit. I think Lenny, I don't think Lenny came back to us one day. We were talking about this. Remember when we were doing math and we had transformer ratios?
Yeah.
Yeah, so I'm just gonna throw one out there, 7,200. And our total output was 240. For the math purposes that we had out there, and to be able to, for me, I'm able to compute it a little bit better. I always put what? 1 to what?
30.
30. And now 30 times 240 equals 7,200. So we're talking about voltage ratios when we were talking about it in this aspect. All right, I'm going to draw another one over here. In real world, in actual physical application, not math application, I've got 7,200 volts and I've got 240 volts. And Lenny, keep me on track here if I get off track. There is actually 30 coils here. And how many coils down here?
One.
One, okay. So in actual physical application, the primary winding has 30 and the secondary winding has 1. All right, for math, we did it like this, much easier to throw in a calculator. For physical actual windings, and I will do one down here in the corner. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 30. 1. That is the actual physical application of coils that are inside a transformer. 30 out there in the world. Does everybody understand that? That's actually what's inside the wires in the transformer. So the question comes up, transformer voltage ratios directly correlate with the transformer blank, kVA, windings, or size. You want to ask that question again?
Yeah.
Transformer voltage ratios directly correlate with transformer kVA, that's the wattage, windings 30 to 1, or the actual physical size of the transformer.
The second one.
Question again. I'm sorry.
Okay, that's cool.
Isn't it the caveat?
So why
Let me throw a little bit more description on that. Okay, 7200, 240. This is winding ratios now, guys. Physical winding ratios is 30 to 1. Okay, that's the actual physical in place. In order for to do the math on it, we went like this: 7200, 240, and then we went 1 to 30 to be able to calculate math. Is there really any difference in the two? Now I'm talking ratios. Is 1 to 30 or 130 to 1? That's a simple question there.
Yeah, it's a difference.
Same thing.
Yeah, it's the same thing. It's just reversed. Okay, it's just reversed in direction. Mathematically, we use this. Physically, inside, we use this. But is there any difference in the two as far as math? I'm not 1 to 60, am I? Or 1 to 45. I'm 30 to 1 or 1 to 30. I'm still going to have 7200 producing 240 volts. If I change any of these numbers, I'm not going to get 240 volts out. So I've got to keep it. Remember, I'm not going to throw something out there that automatically changes voltages on me yet. We'll talk about that later. So as far as the transformer is concerned, I'm going to restate the question again. Transformer, the output voltage, transformer voltages are directly correlate with the transformer kVA. That's predetermined. Size, I don't care how big it is. That's really, or the windings themselves inside the transformer.
The windings themselves.
Windings and
Right,
stuff.
right. Whenever I change the windings, it's going to change my voltages. Okay. 7200 winding wise is all, and 240 out is always going to be 30 to 1 physically in winding amounts. All right, so the windings are going to determine the difference in voltage I have in my input and my output physically inside the transformer. Winding to determine that. kVA, no. All right, so the physical size of the transformer, how tall and big it is, no, that has no correlation to it. The windings are what determines what voltage comes out of it.
So if it was like 1400 kVA, would the windings be like 60 to 1?
No, good question. And I think Lennon asked that question too. You always have to maintain the 30 to 1 ratio, but watch this. So, and I'm not going to use this as a learning process. I don't know the actual ratios. I mean, I know the ratios. I don't know the actual amount of windings that's going on here. So let's do this.
Oh, I think I get it.
30. And this probably will not produce 1 kVA. So 1 is 1 kVA. All right. This is just to be able to do in the math. 60 to 2, is that 30 to 1?
Yeah.
It's 2 kVA. All right. 90 to 3, is that still 30?
Yeah.
It's 3 kVA. You see how this is going on?
Yeah.
I'm applying more windings, but I'm maintaining the same ratio. Now I'm able to pump my power up.
So if the transformer was, say it was 100 feet tall, it would have a ratio of 30 to 1, but in that 30, it would have like 60 blocks of whatever windings.
You would still maintain, what you're saying in your question is, you would still maintain the same amount of windings. Obviously, if I need to add more windings, my kVA is going to rise. I will be able to produce more power with it.
Okay.
Right. Right. That's why you see the transformers on the field that we have are 10s and 15 kVAs. They're relatively small. You start moving it. Well, I think the biggest transformer we used, Professor V might jump into this, was a 333 that you could hang on a pole. I mean, guys, this thing weighs 12,000 pounds, about 6 tons. Okay, there's no difference in ratio between the two, but there's a huge amount of difference in the amount of turns. Ratio remains the same, but I might have 10,000
Right.
to whatever. And obviously, I need to have a transformer in a tank, and it's going to get bigger because of the amount I'm throwing in there. Good question. All right.
So how much weight can we hang off a pole?
How much weight can we hang off a pole? A 333 was typically the max. Now, what we did in that situation was, and it's in ocean lakes mostly, is we took a 50-foot pole. It's a little bit more long, and we cut 10 feet out of the top of it, and we hung the 333 on it. Now these things are huge. All right, and we did a process. Professor V, jump in here if you've ever done this before. We took a guy, put it to here, and it's called a sidewalk guy. Put a piece of conduit, and then put that guy right back to the pole itself. I mean, it's like a bow and arrow type situation.
Right.
So the pole doesn't actually bow where you've got that 12,000 pounds at.
Right.
Professor V, you seen stuff like that?
Similar, yeah. We did similar applications. Yeah, most of just we used the 50 class 2, 50, class 1, just a really large diameter pole to be able to handle that size transformer. So, yeah.
I mean, you look at it, it is quite the sight to see. I mean, you can't.
That's crazy. 6 tons. That's a lot of weight.
Yeah, yeah. It's but you be very surprised at the dynamics of this right here, of not having the pole bow in the middle from that transformer. Remember, I've got conductor up here that's helping hold the pole in place. But the wood itself, to be able to hold a transformer of that magnitude is quite well engineered.
Right.
Exactly.
Okay, so that satisfies quiz 1. Let's go ahead, and we already touched on quiz 2. Let me get out of this one. And we'll review both here by the time we get done today. We might push it to 11.
Yeah, we'll have to probably.
Why did it shoot me all the way out of the course?
Yeah.
No, my word.
Okay, go back.
Stop that share. Okay, get back to ELW 111. Go to tools. What? Tools, quizzes, assignments, quizzes. And go to quiz 3. Okay. All right, the intensity when a conductor is moved. Yep, when a conductor is coiled. Yep. All right, so and I'm go over that one a little bit. We've touched on it before, but let's go ahead and discuss that again. So you've seen this on some of the videos. Sorry, clear all screens. On that video we just saw, the transmission lineman, he had a de-energized conductor here, and over here he had 500 kV with current on it, and that magnetic field was producing voltage over here. You've seen in some of the videos, how can I actually intensify, and think of a transformer, how can I intensify that magnetic field and focus it? How can I make it more intense rather than just a straight conductor end to end. What can I do to intensify that in a smaller space, say a transformer?
Wind it.
Wind it, right, coil it. All right, as soon as I coil this conductor right here, and think of it in this process, this is 200 feet end to end. Once I coil it inside the transformer and get all this 200 feet in one space and coils, that takes that whole 200 feet and puts it in one spot. So I can make an electrical coil. It'll take that magnetic field. I'll have a magnetic field off this whole conductor. Now in this small space, I'll still have that same magnitude or intensity of a magnetic field by coiling it. All right, if you want to see an example of that, let's see. I just looked at it. An example of that is page 105. In that figure 105, you've got a, and they're using a core there. We'll talk more about cores here in a little bit. They've got a core that they're going through, but you'll see one has lesser coils in the space, more has more coils in a space. That shows you that one has less inductance, more inductance. Well, that means I can either transmit or receive more of a magnetic field on it. So that's a good indication of that. All right, when wrapping a coil around, all right, so they're asking it right here. The video that we had before, let me bring up a picture, unshare this one. Clear all drawings and stop the share on that one. Get over here. All right. Oh, the computer's slow today. Core. So there are different methods to get the most efficiency we can around a transformer, to be able to focus that magnetic field and actually get a path of magnetic field flow. So let's get this picture right here. And open image, a new tab. Control plus. You guys might be using some of these in your presentation drawings, and it is perfectly good if you do, because it is a great representation of what a transformer does.
Yeah.
So you'll see, everybody see that image?
Yeah.
Okay. Now I want you to pay close attention here. We just got done talking about it. We're not talking any kind of math in this picture right here as far as the 1 to 30 or 30 or 1, but they are, and you'll notice by the upper description it has on it right here. What are they talking? Primary what?
Winding.
And number of turns. Secondary winding and number of turns. You will notice on the primary side, we're not going to count them, but they've got a high amount of windings on the primary side and a lower amount on the secondary side. So that's my winding ratio that you're looking at right there. Okay. Now, if I just had this, take this block out of the picture. If I just had this coil facing the other coil just like this, I would get transformation out of it. All right, I'd be creating a magnetic field, and that magnetic field would be cutting across this, but that magnetic field would be going everywhere. This way, that way, out the back, out, all around, just like a normal magnet does when it's sitting in space. All right, if you introduce a core, and typically it's an iron core into this, and you wind around the core, that magnetic field, you'll notice by the green arrow, is going to flow along the core itself. So magnetic energy is going to flow along the transformer core. The flow direction is determined by the direction of the windings. If I wound it this way or I wound it this way, and that magnetic field is going to cut across and go through here. All right, so again, and I'll reemphasize these, we're going to talk about this 100 times. Am I creating a magnetic field?
Yep.
Right? Do I have a conductor?
Yep.
Yep. All right. Do I have movement?
Yep.
Yep. AC electricity, back and forth, back and forth, back and forth. So it satisfies all three, and I'm able to produce voltage out of the secondary voltage. You will notice, now this is all insulated. The windings themselves are insulated from each other, and there's no physical contact with the windings to the core. This is just a pictorial representation. They're insulated by paper and oil, all right, but the magnetic field still does flow. So there's no actual physical connection between primary and secondary windings. Any questions there? All right, let me unshare that screen. The share. So the question would be, and it's true or false, when wrapping a coil around a metallic substance, the magnetic field is focused and increased. True or false?
True.
Good. You just saw it. Okay. All right. So, Professor V, when you get a chance over there, can you find a voltmeter, ammeter, and the phasing space for me? I'll go through the last two. All right. So let's talk right here. We got 4 more things to go through. Let's talk a little bit outside and actually how an electrical system is configured. I'm going to go to my whiteboard here. This is, you know, we're actually getting into 112 a little bit now. I like to get you guys, you know how it works. All right, so, and this is going towards your presentations too, working on your presentations. What, on my electrical system, we talked about voltage before and voltage ranges. What two, I don't want to say different types. I'm just going to say it flat out. I've got transmission lines. And I've got distribution lines. Now, for those that are working in your presentations, can you give me an answer? What's the difference between the two?
One's higher voltage.
High voltage, right?
Right. Well, one's at a higher voltage. Okay, good.
Also, don't transmission lines, they like feed distribution lines?
They feed to the substation, and the substation then produces distribution lines, and that is a good thing, right? It's part of the word itself, transmission. It transmits, not like a radio, but it transmits out to substations. Okay, that's the attribute of transmission lines. Now, by your charts and what you've seen with Professor V produced for you in ELW 110, he actually gave you the voltage range. I'll throw it out here. As far as I know right now in the United States, the highest voltage for transmission is 768 kV, and the bottom edge of that is 34.5. You'll hear some companies say that 34.5 kV is sub-transmission. As far as Santee Cooper was concerned, we consider that distribution, anything higher than 34.5 kV. Now, seeing how Lenny brought up, he's going to be working overseas. Right, Lenny?
Anything's possible.
You got that right, buddy. All right. I have heard news that India and some points of China are using a 1.2 MV line. So what does that translate to?
Million volts.
1.2 million volt transmission. That's getting up there, guys. All right, so transmission lines, they're higher voltages. They're meant to go longer distances because of that high voltage, and it transmits from point to point or your generating station out to substations. What are distribution lines?
They distribute the power.
You're right, right. And give a little, I mean, transmission essentially does the same thing. Distribution, it's got a lot to do with distance.
Basically, they bring the power to the service, to the residents, to the factories.
Okay, good, good, good. Service.
Like a carrier service.
Yeah, service to we'll say municipalities, cities, you know, customers, factories, just like you said. Okay. So, and our distance is shorter. We're not going to go as far as transmission does. And we've got to realize too, even though I've got going out on distribution lines, I'm going to have to transform it again to get it to the actual customer.
So it's very low voltage.
Well, we're going in distribution line voltages. So distribution is going to run anywhere from, and boy, keep me right here, Robbie, 2400 volts.
Yeah.
Is the lowest, up to 34.5 kV. So, you know, you're seeing that's the beginning and that's the end for distribution, 34.5 kV. Okay. Obviously, a lot easier to build. I don't need to go as far. And when I get it to the customer, I only need to transform it one more time to get it to the customer's home. Okay. Now there's some different attributes as far as the network is concerned. Sorry about that. Start share. I want to clear this. When we start talking about the transmission network, how our lines are built, and distribution network, when I say that, don't think of internet or anything like that. Think of how I get it out, how I get it to the location I have. There's two different methods in these two processes. I'll start with distribution first. Glad you guys are working on your presentations. I've got a substation and I have a feeder, distribution feeder circuit that goes out, and it might go to different locations out here in the world, down roads and whatnot. Okay. At every one of these points where I stop, you guys remember the symbology for a switch?
Yeah.
Okay. Oh, that was bad. Control C. All right. All right. What is that symbology I've got top? Is that switch open or closed?
Open. Closed.
Closed. Correct. When I
What is it? It was open.
There you go. There you go. Remember that, please. When I keep it like that, that's just to let me know on a map how that.
Okay.
All right. That's just to let me know on a map that a switch exists. Oh, what? Text. And excuse me. That just lets me know on the network that a switch exists. That lets me know that switch is there and it's open. Okay. So in distribution lines, what I will do as far as my network and how I lay my wires out onto my system is I will have my wires going out, and like there's tap lines coming off of here, and there's transformers hanging on it. So I'm feeding everybody along this circuit. And this is my substation breaker. All right, I've got another substation way over here, got a breaker, and I got my other feeder circuit, and it might do this. Go down this road, go down that road, finally come up to here, and it's going to go down this road, pass by here, go down here, and come up to here, come way over here, down this road, it might even tap into there. You'll notice, and this is where I'm headed to, guys, when the line goes out, it comes and stops at a point. Here's going to be my question. Is it radial? Does it go out and stop? Or at this time, the way you see it, is it loop? Now, looped means it can be fed from multiple directions at the same time. Radial means it goes out and it stops. So the system that I have drawn here, is it radial or looped?
Looped.
Do I go out to this point and stop?
No.
There's an open switch right here.
Oh, sorry. Yeah.
Do I go out to this point and stop?
Yeah.
Okay. Do I go out to this point and stop?
Yep.
Vice versa, you'll notice it does the same thing from the other direction. Goes out to a point, stops. Goes out to a point, stops. That is radial. All right. If I take a line and go down to here and stop, just end it, that's radial. Same thing with distribution circuits. Okay, so the question will come up. A utility distribution circuit is normally blank, radial or looped. Radial goes out to a point and stops. My question, a utility distribution circuit is normally radial or looped.
Radial.
Radial goes out to a point and stops. That's its normal operation every day. Hang on, guys, we're almost finished. All right, let's talk transmission. Here's my generating station. I'm just going to draw it in a circle. And we'll put some substations along the way. Okay. All right, so that's a sub 1, sub 2, sub 3, sub 4, sub 5. Okay. And prior to and leaving from, I'm going to have a circuit breaker on each side of the substation. Now you'll notice by my symbology here, are there any open points? Do I have any O's?
No.
No, so I've got breakers on each side of my substation, but I have no O's. Is this system radial or looped?
Looped.
Looped, okay? For one, you got a big loop in it. All right, transmission is normally looped. And the concept here is, guys, in distribution, if I have an occurrence on my circuit, I'm going to have protective devices. I can go out and fix it and be there relatively quick. It's a short distance. In transmission, I might go 30, 40, 50 miles. And these things are going to be in swamps and woods. Think of this concept that happened. Well, it's not a concept. It actually happens out there. If I have a circuit breaker here and a circuit breaker here and a tree falls in the line, how much power do I have out?
All of it.
Just between the breakers.
Just between the breakers. None of your power has gone out. I've got indication. My dispatcher knows, hey, this breaker just tripped open. This breaker just tripped open. But nobody has lost power at all. It's not that like they're going to say, well, I'm going to take a little time to get to it. They're going to get to it as quickly as possible. But as far as your customer base is concerned, they haven't seen anything. Okay. So that's why transmission normally runs a looped system. Now, we typically don't do this in distribution. This takes a lot of expensive equipment to do. And the other reason is long distance and accessibility. Okay. So question. A utility transmission circuit is normally blank, looped or radial?
Looped.
Looped. Fantastic. Okay. Professor V, you ready to roll?
Ready, buddy? You ready?
Yes, sir. Let me unshare this. Okay, so we've talked about it, transformers, and it's time to get our learning hats on right here of voltages, measuring amperages. Professor V is going to go over the actual tools that we use.
Okay, everybody see my screen?
Yep.
Yep.
Okay. All right, guys, this is AC or DC voltmeter. It's used to check voltage on mainly secondary lines, not primary. You can see this meter, some of them out there go up to 600 volts. This meter looks like it goes up to, can measure up to 1,000 volts. You don't want to really go over the voltage, that level of voltage, or you're going to have a catastrophic failure of this piece of equipment. Down here, you can see the symbols, and I'm gonna keep it enlarged so you can see it good. You got, of course, you got your off button, and if you leave it on, it does have a timer that it will cut off after a certain amount of time to save the battery. So anyway, your first, and it's I think this one is a multimeter, but your first selector right here, see that little squiggly line above the V? That's for AC voltage. Is that correct, Professor Shoemaker?
That is, I mean, that's your sine wave. That lets you know it's AC.
Correct. And that's what you want to check your voltage with, neutral or ground to phase. And guys, do you think it matters if you switch the leads around and put the hot leg on the, your red leg on the ground and your black leg on the hot leg? Does it matter on AC voltage? DC, AC?
No.
No, it does not.
Right, because it's bi-directional. Good answer.
Correct. It'll give you the same reading either way. Good piece of equipment. Fluke makes an excellent voltmeter. That's all we used at Duke. Your next selector up here, if you wanted to check DC voltage, if you wanted to check batteries, whatever you're working on, you can see it's got the little solid line on top with the intermittent lines right up under it. So that's the two main voltages selectors that you would use on a voltmeter, mainly the AC voltage. Like I said, you just want to use this on secondary voltages, not anything over 1,000 volts.
Yeah. Check your meter, guys. And that's a fluke. We use flukes when at our company.
Yep.
Expensive. Boy, these things are, $500-600 a piece.
Yeah.
Very precise. But if you get a voltmeter and you don't know what the range is on it, pull that yellow cover off. It's written right on the back. Voltage range 0 to whatever.
Right.
Don't go over that range.
Right. Let's see what else we're going to say about it. It does have a hold button on it. So, you've only got two hands. So if you can't hold the voltmeter and it has to sit on top of a meter base or something, we're not able to look at the screen while you're checking voltage. You can mash the hold button, put your leads on it, and it'll actually hold that reading until you clear it out so you can know what the voltage is. Very good piece of equipment here.
Yeah.
Do not want to use this on primary.
Yeah. The only way water, I wouldn't say waterproof, very water resistant.
Yeah.
What do you think would happen if I was actually checking AC voltage at 480 volts and I had it in the DC position? Would it blow the meter up? Voltmeter.
I don't think it would blow it up, but I don't think it would read anything.
It's not going to read correctly as long as you don't go over the rating of the meter.
Right.
And it's just going to, the new ones now, they're going to throw up that says ERR.
Yeah.
Right. You go to any of the wrong readings for what you're trying to apply it to, it's just going to give you and let you know you're not in the right position with your knob.
Safety aspect, as far as the voltmeter go, guys, if you're up a pole working on secondary voltage, would you be wearing your rubber gloves working on secondaries?
Yep.
Okay.
Yes.
Would you be wearing rubber gloves handling these leads, checking voltage?
No.
Yeah, you would, because you're still handling secondary voltage, but with smaller leads. We weren't allowed to wear leather gloves or anything like that. We had to wear rubber gloves when checking voltage due to the fact that this is a piece of equipment that gets moved around in your truck. It gets, carried from meter base to meter base, from transformer to transformer, up in the bucket. And those leads have a chance of getting damaged, and you do not want to, put your hand on any raw wires on those leads or touch the tips of them, because they do become energized as well. So safety wise, rubber gloves.
Yeah, I saw a guy one time take one lead, and it was a small space. It was a small meter base, and he was trying to prop the meter up on the meter base. He took one lead and touched it to the energized wire coming in the meter, And guess where the other lead was?
Ooh.
On his finger.
He was holding in his mouth.
Mm.
Okay, guys, remember, difference of potential here. Your mouth and your feet on the ground is going to be the new path for current flow.
Yep.
That meter does the same thing. It's a conductor, so treat it as such.
Yep. And really the last thing to go over, I want to go over with the voltmeter is replace the batteries in it every, month, 2 months, or how often you use it. Because if you have weak batteries in it, it's going to give you a real screwy reading on it. And you're going to be scratching your head.
Yeah.
Why am I getting such a reading on it? Change those batteries regularly. Keep fresh batteries in it. Very important. Okay. Any questions about the voltmeter?
So what do we use to measure voltage with? Voltage.
A voltmeter.
Hey.
Yep.
Okay.
Okay.
Yay.
Marty.
Marty.
All right. Can you guys see this one, this next meter?
Yep.
Guys, this is actually another voltmeter, or it's an amp meter. Is this a voltmeter too?
It's a multi. Yeah.
It's a multimeter here as well, but on the top of it, it has jaws for reading amps on a circuit.
I'll try to
Wires,
take care of that.
conductors. As well, it has a selector on it where you can check your AC volts on it. It does an auto selection on it when you're checking voltage, and you can see by the little voltage symbol there with the squiggly in the straight line that it'll detect whether it's AC or DC. It has a ohm symbol on it where it'll check for continuity. It'll have a little bell on it. You can hear it ring when you want to ring out wires to make sure nothing's crossed. If you do have wires crossed in a meter base, you want to be sure and check that. It'll actually give you a little tone and let you know, hey, you've got wires crossed up in there and you need to check them out. But the biggest thing you want to look on here is your amperage. If you're trying to check amps on conductors coming in out of a transformer, and this is very important to remember, guys, you want to check one wire at the time in it. You do not want to put like a neutral wire or a energizer conductor in it, because it's going to cancel each other out and it's going to give you a 0 or near 0 reading. That's very important. That's going to have you scratching your head. And then especially if you go into like a pad mount transformer, when I say pad mount, that means like on the far end of our yard out there, there's all those green boxes. Well, those can become tightly packed with conductors in them. You're trying to get an amp reading on a certain conductor in there and you're having to pull wires. You just want to make sure you get it on your right wire. Make sure you have the jaws firmly closed, because it's going to what it's doing is picking up that magnetic field around those conductors, and it's going to show you how much current's being, is flowing through that wire going to that customer's home or whatever it's serving.
I'm glad you brought that up. I mean, these things are pretty precise, especially in the fluke line, very precise. There's no physical contact going on in here, so I can use this up to whatever voltage I want to.
Right.
I'm not going to a conductor and then the ground. The jaws right there, doesn't matter where you have the wire in the jaws. It's measuring the magnetic field given off, and a magnetic field, that just goes back to what we were talking about before. The more current I have, the more intense the magnetic field. One question I do have for you guys: does it matter which direction I turn it? Can I have the numbers facing away, or does it matter? Can I turn this thing, can I clamp this on the wire right now and get a good reading? Flip it over, clamp it on the wire again, and still get the same reading?
I would assume so.
Yeah, and the electricity flows both directions.
Right.
Yep, you're right. Doesn't matter which direction it faces.
Yep. Questions about the amp meter? It's a very good tool to use, especially if you're trying to, if say you have a customer that's out there and wants a service disconnected out of a transformer, and there's 5 or 6 services in there and there's no current, you've pulled a meter on that service. There's nothing going to it, no flow going to it. You can take the amp meter and start clamping around your conductors one at a time. The one that has no, that you know that has no flow will be more likely 99% of the time will be your conductor you want to disconnect for.
Yeah.
So good piece of equipment.
It is.
Yep. And I think I do have one of these in the back of my pickup truck if you guys want to
Yeah.
put your hands on it tomorrow.
And you know, we have talked, we've gone over the voltmeter so far. So we've talked secondary voltages. That's how I can determine secondary voltage out of transformer when we did our math ratios. This I can use on any voltage. So I can check my current flow up. This will go around a fuse barrel.
Yeah.
It'll go right around it. I can actually check the amperage through a fuse. I can put it right around the conductor. So now we're figuring out, well, how do I get that reading? This is what you clamp on. Obviously, you got to use rubber gloves.
Yep.
And you've got to be in an insulated device to do it.
Right. Okay. So what was the question concerning that?
An amp meter is used to measure what?
Yeah.
Wow, that's hard. Yeah.
I had to think about that one.
Yeah. Let me hold on a second. I'm looking at it right here as the question. I'm not looking at the answers. Hold on. Okay. An amp meter is used to answer secondary measure secondary voltage, primary voltage, secondary or primary amps or line resistance. And you guys have already answered it. Secondary or primary.
Very primary.
There you go.
Any other questions about the amp meter?
You said it was primary amps, right?
What was that, Jordan?
It was primary amps, right?
Primary, it'll check anything.
Primary or secondary?
Primary,
Okay.
secondary, transmission, distribution, anything you want to put it on. You just got to use the right safety procedures when you're using it.
Okay. All right, I guess the last piece of equipment we're going to use is look at the piece of equipment used to check primary voltage. A little bit different piece of equipment. It's actually, and you can see this picture here. I've got it. Make sure right there. There you go. And we actually have some of these in the trailer if you guys want to look at them, and we'll get into more of these in a little bit more in depth in the underground. But these are what we call primary Hastings phasing sticks. They're digital voltmeter. And guys, they good piece of equipment to use to check your different phases, check voltage on the line. Just good video. I got a video, Professor Shoemaker, if you want to look at the Hastings video.
That's your call.
And I mean, we can look at this and we'll skip through it. If you have any questions about it, just stop me. We'll stop and talk about it. But these guys do a pretty good job of explaining how the Hastings phasing sticks work and how to use them.
I'm John Saka, and this is Kirk Mulder. We're out here today to do an actual demonstration of phasing a distribution circuit. All of our safety equipment's ready to go, our harnesses, and rubber gloves, and sleeves. And we're going to actually do the procedure right now. Well, Kirk, if you're ready, let's make sure that we have voltage on both sides of these open switches. And we'll go road phase to center phase, road phase to field phase, and then center phase to road phase, and center phase to field phase. And then we'll do the same thing on the bottom side of that cutout. We'll have this phasing procedure completed. We can close this feeder together. You ready?
Pause it there, Professor B?
Go out on a line.
Okay.
So right now in their process, because they're actually doing phasing, they're going to measure from one primary phase to another primary phase. You can use the sticks from one primary phase to ground. But in the video, you're going to see a voltage reading that shows them a phase to phase voltage. And before we proceed on, it's 7,200, right?
Correct.
Okay. It's a 7,200 phase to ground voltage. Watch what they get on their phasing sticks when they measure it. Go ahead.
Mine a little bit to keep that cold cord away from that ground.
So he touches
I
one conductor.
have 12.5 here.
Pause it. All right, 7,200 and 7,200 on two different phases equals what?
So right there, 12.5.
Why is it not 14,400?
Because of the impedance.
No,
Mm-mm.
but you're thinking caps of what we talked about yesterday, the day before yesterday.
Oh, because the electromagnetic field.
Two sine waves cannot be in the same position at the same time, right? I'm using two different phases here.
What's that magic number?
What's the magic number?
It was like 1 point. I got 1.7325.
There you go. So if I took my 7,200 and if I multiplied it by 1.7325, I should have 12,470. Now the sticks are going to round up. So as soon as I hit 12,450, 12,450, that stick is going to say 12.4. As soon as it goes above 12.450, that's say 12.5. It is
12.92.
right.
12.5, yes, sir.
Right. So that is 12.5 kV, kilovolts, not 12.5 volts. Go ahead, Professor V.
Okay.
Hey,
Yeah.
12.470 is logical. I'm going to go out to that node phase. Do you want to pull that cord down just a little bit? Yeah, very good. I'll go on the bottom side of this stirrup and get a little more clearance. Road to field, I'm seeing 12.4, which is phase-to-phase voltage. So that's showing good. Just for security, let's go to non-metered in for that center phase out on top. And I'll go to the field phase. And I'm seeing 12.5, so that's a phase-to-phase voltage. You ready to check the bottom side of this head out?
So now he's going to check the wire coming from the other direction. You'll notice there's nothing in the switch.
Just rolling your cord up to control that cord a little bit. Oh, that's a real good idea. That'll keep that away from the ground potential and give us a more stable reading. The bottom side here, I'm seeing 12.4, which is acceptable at the phase-to-phase voltage. Oh, you want to go to that field phase, the road phase? I'm seeing 12.5 here, Kirk, so that's a phase-to-phase voltage. Check it across.
All right, see guys, what they were doing there, just to kind of give you a better understanding what Professor Shoemaker said, what these guys are saying before, when they were hanging these hooks on this side, they were hanging here, and on this other side, they were checking this side of the pole. Going to the bottom side, from bottom side switch to bottom side switch, they're actually checking voltage on this side now. This jumper's coming around to the bottom of the switch, kind of being, it's kind of a good idea as far as safety goes to do that, because you're actually not having to reach through these phases to this side to check it. They can get it from the bottom of the switch to the bottom of the switch. A little bit easier for them.
Yeah. Before you carry on, stop it when they start going across the switch. I mean, you know we're going to ask.
Field and road phase. All right. You ready? I'll pull that cord down a little bit. Very good. Well, I'm seeing 12.5 here, so that's a phase-to-phase voltage. These circuits are hot on both sides of that switch.
All right, here we go.
While you're there, why don't we just go across that open switch you're at?
All right, pause it.
Got it.
Okay, gentlemen, question. So they're working, hopefully and expectedly, with the same phase. I don't know who that person is that keeps unmuting themselves. That would be Jordan Clark. Jordan, I just do that because you got a lot of feedback on your stuff. So if I'm going to measure same phase, went phase to phase, they got 12.5 kV. 7,200 times 1.7325. If I'm going phase to same phase, what should my voltage reading be? Anybody?
Probably the same, right?
Same phase. He just went opposite phase, 7,200 to 7,200, and we used the 1.7325 number. All right, now he's going to remeasure. Let me put it to you this way. If he took the stick on the left and put it on the conductor, and he took the stick on the right and he put it on the same conductor, what should his voltage reading be?
12.5.
Same conductor.
It's the same thing.
You see a little, hover your mouse over that box, right? The stirrup, Professor V.
Right here.
Yeah. If you put both hooks in that stirrup, same wire, what should his voltage reading be? Is there any difference in potential? There you go. That's a good question.
Yeah.
Is there any difference in potential?
No.
What should his voltage reading be? 0. I heard it. I think that was Nigel. 0.
I was unsure of that.
Yeah. If there's no difference in potential, gentlemen, I'm on the same conductor. There should be 0 voltage reading, or there's no difference in volts. Okay. So go ahead, Professor V.
Well, let me pose another question.
Sure.
In this situation where they're checking from here to here, why do they need 0 volts there, guys?
Good question.
What if he checked voltage here and got 7,200, 7 point, or 12.5?
And
What would be the situation?
I mean, it definitely showed that there's a difference of potential, and that's not good.
That is
Right.
Exactly.
Right. He would be going, if they close that switch, they'd be going phase to phase. You'd have a major explosion. Good one, Lenny.
I'm seeing a 0 voltage there, Kirk. That's the
Bingo.
same thing.
That means I'm working on the same conductor. Now we'll ask Ryan Embry this when he gets to the last one.
And I'm seeing 0 at that location, so that's the same phase.
Oh, I see now.
Mm-hmm.
And at this location, I see a small variance
Okay.
of 100.
All right. So what's that voltage reading?
0.2.
How many volts?
2 volts.
Volts. If it's 1.2 kV, that's 1,200 volts. That's a 0.2. So how many volts?
Oh, I'm sorry. I'm sorry. So the meter is in kV range.
It always stays that way, correct?
I'm sorry. So it's probably 200 volts.
You're correct. Correct. Great. Yeah. That was a good thing to notice there. It always stays in kV range. So I got 200 volts difference between these two lines. Ryan Embry, why? You like to say it all the time.
The foggiest idea.
Huh?
I don't have the foggiest clue.
Impedance. Now we got line impedance.
Oh. Switched it up on me.
Yeah, you got line impedance on this other line that's showing a little bit of differential in the voltages, okay? And that's why you're getting a 200 volt difference of potential. Is it still the same phase? Yes. But line impedance is giving you a little bit of a difference in voltage reading. Go ahead.
You ready?
Yeah.
Fluctuating to 200 volts, which identifies it as the same phase. You know, on a lot of feeders, when they want to take it off, if you've got small wire coming out of a substation and it's a heavily loaded circuit, and one side of the switch is a large wire pulse to the substation, it's conceivable we can have a fairly high reading on the same phase, but still go together. I've seen 500 and 600 volts
Okay.
on a distribution circuit.
Yeah, that's the difference with a digital meter
Because-
over an analog.
So, I mean, he uses a little bit of line terminology there. When he says it can go together, means it's the same phase.
Yeah.
But he gave, I like his little bit of description there. He had a small conductor out of a substation, which had a high impedance because it's small. And then he had another conductor out of another substation. How he gave a pretty decent description.
Right.
So, question 10. What is used to check primary voltage? So, what do you see in the description or title of this video that you just saw?
Phasing sticks.
There you go. Phasing sticks. Primary phasing sticks. I've seen it tried.
Phasing sticks.
Yep, I've seen it tried once before where we told a guy, and I don't know what was wrong with him. We told the guy to go up there and check the secondary voltage on a transformer. And guess what he did? He put one lead to the primary, and he put one lead to the grounded bushing on the transformer with a voltmeter. Guys, it was a pure meltdown. Know your equipment, right? Once you have a voltmeter, know the range of it. And once you go out of secondary voltage into primary voltages, then you're going to move to the phasing sticks.
Yep.
Okay.
That's 3.
Wow, that was a lot of meat and potatoes for today.
Yep.
Any questions? All right. Well, Professor V, anything more you'd like to add?
No, sir. Look,
Okay.
that was good review and good videos.
Yeah, man. So once again, we are gonna, I'll text you and let you know, quiz 2 and quiz 3 are going to be available today, starting at when I text you, and they will be open until Thursday midnight. Not today midnight, Thursday midnight. So that gives you plenty of time to complete both. Questions by anybody?
I got one question, Mr. V. What we talked about yesterday, if we can kind of go over that.
Okay.
If that's
Okay.
possible.
Yeah.
Yeah,
Okay.
yeah. Professor V have made me aware of that too, Nigel. That's no problem.
Yep.
Okay.
Jordan,
I
I saw some noise come up on Jordan, but you were muted. George, you have a question?
No, I'm good.
Okay, buddy. When you get a chance, check your settings in Zoom, and you're really, sometimes you're distorted. You're so loud.
All right, I will do. Cause I was wondering, cause I just got into bed. There's no noise back here, so I was like, I don't know. I wonder what's. Yeah, it's probably my settings or something.
That's a little bit too much detail for me. I mean, I got a video on that, but
My bad.
all right. Okay. All right. With that, guys, we'll go ahead and close, and have a safe day today. Weather permitting, which it does look good. We'll see you on the field tomorrow, 9 a.m.
Yep.
All right.
Good one.
Have a good day.
All right, guys.
All right, Al.
Yes, sir. I had to go put some money on my lights.
Huh?
Put some.
Oh.
God, my Wi-Fi when I had prepaid lights, and my phone won't do like regular shit.
Oh, so you have prepay? Were you with Santa?
Yes.
Cruz?
No.
Electric.
Okay. I didn't know they did prepay. Okay.
Yeah.
Well, I mean, you missed a good portion of it, but it will be on the video for today. Okay.
I apologize, sir.
That's okay. You still got the video to study on, and like I said, we're available in the afternoons.
Okay, well, I guess